Hi everybody, Dr. Gray here. Today we are going to have our last lesson around gas laws. And today what we're going to talk about is what's known as the ideal gas law. And so an ideal gas is a gas that perfectly obeys those assumptions of the kinetic molecular theory. Not all gases will perfectly obey all of those assumptions, but for our purposes, we're going to assume that they do, right? We're going to think that all gases behave as ideal gases. And so the ideal gas law allows us to determine something about the pressure or the volume or the temperature or the number of particles of a given gas, assuming we have some other information about those. And so the ideal gas law makes use of those three laws that we talked about before. The ideal gas, before we looked at Avogadro's law. Avogadro's law said that the volume of a gas varies directly with the number of particles, or moles, of a gas, right? More gas particles means more volume. Yeah, that's a big no-brainer. That's why balloons work. Boyle's law said that the volume of a gas varies indirectly with the pressure of a gas. And so, as the volume increases, pressure decreases. The third one we looked at was Charles' law. And Charles' law looks at the relationship between volume and temperature. And Charles' law says that the volume of a gas is proportional to the temperature of a gas. So these three ideas get combined together. How does the volume of gas change, or how is the volume of a gas affected by particles, pressure, and temperature? And so we see that we see the influence from Avogadro's law in this first section, right? Volume is proportional to number of moles. We see the Boyle's law that volume is proportional to the inverse of pressure. We also see evidence of Charles' law that volume is proportional to temperature. And so we could combine these three things, right? We could say that volume is proportional to number of moles times temperature not equals, let me fix that, is proportional to number of moles times temperature divided by pressure. But we don't want a proportionality. We want an equal sign. We cannot do calculations with proportionalities. We can only do calculations with equalities. And so to turn that proportional symbol into an equal sign, we have to introduce a constant, right? Now, this constant is not called K. This constant is abbreviated as a capital R because it is the gas constant. And so if we introduce this gas constant, then we can change that proportionality symbol into an equality. And so now this equation, the V is proportional to NT over P, becomes a equality. When we can put that as an equal sign when we say, we're going to throw R in there times NT over P. Well, that's pretty messy, so let's clean it up. This would become V equals RNT over P, but nobody likes fractions, so let's get rid of the fractions. This equation rearranges to the ideal gas law, which is that PV equals nRT. All right? And so this is the other formula, the other law that we have to work with. Now, the first thing that I want to point out about this law as it relates to the combined gas law, which is the one that we did before, right? So our combined gas law is P1 V1 T2 equals P2 V2 T1. This one is known as the combined gas law. Notice the difference between these two equations. In the combined gas law, you're going to end up with two values for pressure. You're going to have the potential for two values for pressure and two values for temperature and two values for volume. In the ideal gas formula, there's only one of each. And so if you're trying to decide which gas law will I use, look at the data you're given. If you're given two sets of data for pressure and volume or temperature, you would use the combined gas law because that's where you're going to use two separate sets of data. If you're only given one set of data, also if you're given any information about number of moles, then you would use the ideal gas law, not the combined gas law. Let's look at a practice problem or two. Nope. But before we can talk about, before we can get into those practice problems, we've got to talk about what is R. So R is that gas constant. And the gas constant would be, what we think about is, what would be the value for R of any gas at standard temperature and pressure? Well, 1 mole of any gas at STP occupies 22.4 liters. And so if we're talking about what is the value for R, for that gas constant, when the pressure is in atmospheres, we would use 0.0821. But remember, we have multiple ways of measuring pressure. We could measure pressure not only in atmospheres, but in millimeter of mercury or in torr. Well, if our pressure is in millimeter of mercury or torr, we would want to make sure we use the correct gas constant. We want to make sure that those pressure units match. And so if the pressure is in torr or millimeter of mercury, the value for R is 62.4 instead of 0.0821. On the other hand, if pressure is given in kilopascals instead of atmosphere, torr, or millimeter of mercury, then we would use the third option, which would be R would be equal to 8.314 if the pressure is in kilopascals. These will make a little more sense as we work through these problems. This first one, the 0.0821, that is the most common one we will work with because most of the time pressure is going to be in atmospheres. We will occasionally use the 62.4 because occasionally the pressure will be in torr or millimeter of mercury. In this class, we will probably almost never use this last gas constant, but it is an option that's available to us. In other units, if we were to get that far, this one would become much more popular. But for now, it'll be these first two values for R that is going to be most likely. So here's our first practice problem. It says, what is the pressure? All right, what is the pressure is my question. In atmospheres, right, so that's the unit it's specifying how it wants us to calculate it, exerted by a 0.5 mole sample of nitrogen gas. So 0.5 moles, that is N. Anytime you see moles, that is the value for N. N stands for number of particles, and we measure number of particles in moles. And so we have 0.500 moles of nitrogen gas, so that doesn't really matter for us right now, in a 10-liter container, 10 liters, that's a measure of volume, at 298 Kelvin. 298 Kelvin, well, that's a temperature. And so when we look at this data, right, you've got pressure, number of moles, volume, temperature, and you only have one of each. And so that means we're going to use the ideal gas law, PV equals nRT. But in order to use that ideal gas law, we need to have one more piece of information. We want to solve for P. We've got N, we've got V, we've got temperature. We would need to go choose which R we need to use. So we have to have R as well. Now, when you go back and you look at those possible values for R, you want to pay attention to what is the pressure unit that's associated. This particular question says we want to know what is the pressure in atmospheres. You want the answer to have units of atmospheres. The only way that can happen is if you use the gas constant with atmospheres as the pressure unit. And so our value for R in this problem is going to be 0.0821 liter atmospheres per mole K. And so now we have all of the information we need in order to solve this problem. But as with the other one, I recommend that you rearrange this formula first and solve it for the variable you're being asked about. We want pressure. And so we want to get pressure all by itself in this equation. We do so by dividing both sides by volume. So pressure is equal to nRT over V. Now it's just a matter of plugging in the numbers and checking the units to make sure things work out. We've got N is equal to 0.5 0.500 moles. R is 0.0821 liter atmospheres per mole K. T is 298 Kelvin. We divide all of that by the volume, which was 10 liters. Now is a good time just to make sure that things are where they belong and that you're going to get the answer or the units that you're looking for. And so we check. Moles cancels moles, kelvins cancel kelvins. That leaves us with liter atmospheres in the numerator of this fraction and just liters in the bottom. Liters cancels liters. It's going to leave us with no other units other than atmospheres, which is good because that's what we are looking for. We want to know what is the pressure going to be in atmospheres. Then you plug them into the calculator. 0.5 times 0.0821 times 298 divided by 10 gives us a pressure of 1.2 atmospheres. Let's look at this one. What is the volume in liters of 0.25 mole of oxygen at 20 degrees Celsius and 0.974 atmospheres pressure? So what is the volume is our question. N is 0.250 moles. Temperature is 20 degrees Celsius. It's in Celsius, can't have it in Celsius. Add 273, that's 293 Kelvin, must be in Kelvin. And pressure is 0.974 atmospheres. Only one set of data, so we're working with PV equals nRT. We want to find volume. We're going to need R. What is the value for R? Here, because our pressure is in atmospheres, we're going to choose the value for R that also has units of atmospheres, which is going to be that same 0.0821. Then we're going to rearrange our equation to solve it for volume. So we're going to divide both sides by pressure. So we end up with our formula looking like volume is equal to nRT divided by P. Plug in values. 0.250 moles times 0.0821 liter atmospheres per mole K times temperature, 293 Kelvin, divided by pressure, which was 0.974 atmospheres. Check your units first. Moles cancels moles, kelvins cancels kelvins, atmospheres cancels atmospheres. We're going to be left with units of liters, which is good because we're trying to find volume. We plug those values into our calculator, and the answer we get is 6.17 liters. We have one more calculation to try out. What mass of chlorine gas in grams is contained in a 10-liter tank at 27 degrees Celsius and 3.5 atmospheres of pressure? The question is, what mass in grams is contained in a 10-liter tank, so 10 liters, that's volume, at 27 degrees Celsius? Well, that's temperature. It's a gas. We're talking gas laws, so we're going to change that to kelvins. And 3.5 atmospheres of pressure, so 3.50 atmospheres. Well, we only have one set of data, so we're probably going to be working with PV equals nRT. But when I look at that formula, two things stand out to me. One, I need a value for R, so we got to figure out what that one is. The other thing that I notice is that there's nothing in that formula about mass. We've got volume, we've got pressure, we've got R, or will in just a moment, and we have temperature. What we don't have information about is N. N is number of moles. But remember, we know how to get from moles to grams. And so the first thing we're going to do is find moles. That's our first goal. And then once we know the moles of chlorine gas, then it's a simple matter to convert it to grams of chlorine gas. But before we can figure out moles of chlorine gas, we have to choose our gas constant. Notice that our pressure is in units of atmospheres again, and so 0.0821 liter atmospheres per mole K is the correct choice for for the gas constant here. So in this case, the first thing we want to do is solve for number of moles. We want to solve for N. And so we solve for N by dividing both sides by RT, so that the number of moles is equal to pressure times volume divided by gas constant times temperature. We plug in our values. Pressure, 3.50 atmospheres. Volume, 10 liters. R, 0.0821 liter atmospheres per mole Kelvin, times temperature, which was 300 Kelvin. Verify units first. Kelvins cancel kelvins. Atmospheres times liters divided by liter atmospheres per mole. Liter atmospheres is going to divide out liters and atmospheres, which is going to leave us with 1 divided by 1 over moles, which equals moles, which is perfect, because that's our goal, is to get to moles of chlorine gas. We plug those values into the calculator, and we get 1.42 moles of chlorine gas. Then we have to change moles to grams because it's asking what mass, and so 1.42 grams of chlorine. We want to get rid of grams. Oops, I wrote that wrong. Let me fix that. We have 1.42 moles of chlorine. 1 mole is equal to the formula weight for chlorine, which is going to be 70.9 grams. And so that is equal to 100.7 grams of chlorine gas. So now, let's come back to that tanker car. What have we figured out? Well, according to the video, that pressure tanker initially was pressure washed with steam. So it was washed with hot air, or with hot water, excuse me. And when it was initially washed, the door to that tanker was open. So as the steam was being used to wash down the inside walls, the steam was pushing out some of the air, because now we're adding new particles in, the door was open, and so some of those gas particles spontaneously moved through the opening in that container. We had some effusion happen. After the cleaning was done, the workers got out and closed the tank. The door was sealed. But remember, the inside of that tanker was cleaned with hot steam. The outside of that tanker is cooler. And because that tanker is made out of a metal material, the gas inside would have cooled down shortly after the hatch was cooled, right? So we have washed with steam, which is H2O in its gas form. The steam pushed out air while the hatch was open. Because at a given pressure and temperature, the number of particles of any gas is fixed in terms of its volume. After cleaning, hatch was closed. So now no particles can enter or exit the inside of that container. But because it was washed with steam and it was cooler outside, eventually the air inside the tanker cooled down. And so because the air inside the tanker cooled down, it is now not the air puppies, the air particles inside the tanker are not colliding with the inside of the tanker or the wall on wheels as frequently. They're also not colliding with as much force as the air particles that are on the outside of that tanker. That means that the particles of air on the outside of the tanker exerted more collisions per area than the air particles inside the tanker. And those collisions on the outside caused the tanker to collapse. And so that is why that tanker collapsed. The weight of the atmosphere caused it to be pressed inward. That is all. If you have any questions, please get in touch.